if you're getting stuck, there's a hint right here. This is what you would find in that cookbook. So these are the divergence and the curl.
You just want this uploaded to the drive, right?
Yeah, and if you have it finished, go ahead and upload it and then start on the next one. All right, so this is first one we got. So let's take a look at this first one together. All right, can you all see this well enough? Hopefully. All right, so is this the divergence? Is that what the first one is right here?
Right, so the first one is divergence. Yeah,
All right. So and then is this 2x minus 2y?
2x minus 2x.
2x minus 2x. All right.
That
Who
Zero.
else? Yeah, who else got this? What do you think? Did anyone else finish this one? Daniel?
I kind of did it differently.
Okay. So you got a different answer?
Yeah,
Yeah. What did you get for the divergence?
I go 4x.
4x. Okay. So we got answer 1. Did anyone else get an answer?
I also got 0 for that one.
Okay. So we got a couple people with answer 1, one with answer 2. Did anyone else get something different?
I got the same as
Yeah. You got the same as someone else, AK?
I just
I said I
instead of subtracting.
Yeah, sorry. Daniel, are you okay with being called Daniel?
Yeah, that's fine.
Okay, because I think both of you go by AK. So, which I never expected to have this situation with multiple AKs, but it's kind of fun. Okay, so I'll try to call AK Almaty AK, and then you Daniel, if that's okay with you. Okay. All right, so let's check to see what it should be. All right, let's check to see. Let's make a case for this. All right, so we should take this vector. Take the divergence. Okay. Okay, so oops, and this should be 0. All right, so right, if we look at this, right, this part would be AX, right? This is the magnitude in the X direction. And this is AY. So we can write like a standard vector, right? We would write as X with X magnitude, Y with Y magnitude, plus Z with Z magnitude. So that's where that's how I pull each one of these two things down to here. All right, so then that gives us, what is this going to be?
2x.
2x, yep. And then this one, what is this one going to be? Oops, and this should be minus, right? So then I should get plus, right, minus 2x. I'll make that look like a 2. plus 0. Okay. So I am getting 0 out of this, which I think many of you got. Okay. Now, should we call this, it asked us if this is solenoidal. So should we call this vector? Or should we call vector A solenoidal?
Yes.
Yeah. Yep. Yeah. I like that, Gabriel. Give me the thumbs up. Yeah. So thumbs up. This one's solenoidal, right? And it has a divergence of 0 at all points. Could you have a vector that has a divergence of 0 at some points, but is not solenoidal? Yeah, definitely, right? We could come up with something that is a function, right? Let's imagine. So I'm gonna give this cross this out, right? But let's say it was 4x. Is there a place where vector field 4x is solenoidal?
Yeah, 0.
Yeah, so everywhere where x equals 0, that entire place, that would all be solenoidal in that case, right? But it's a limited subset of places where it's solenoidal. All right. How about for the curl? Who else got this? Yeah, give me a thumbs up if you got this. Same thing. So curl, yes, no. What do you think? Can you read it? Is it too hard to read? What about this format even? So let's just check. Does this say 0 minus 0 plus 4x squared y? Is that correct?
Yeah, that is.
Okay. So what do you all think? Let's just even look at this and think about if it looks good. I don't know. How about, okay, do you think the format of this is correct? When we take the curl, should
I
you,
would probably change the signs.
you would change the signs, Daniel?
Yeah.
Okay, which sign would you change?
That would be the -4 into the -4x squared y.
Okay, so all right, so you're saying maybe this one should be minus here. Yeah. What about, should this be a scalar
No,
or a vector?
vector.
Okay, so it should be a vector. What is this written? How is this written? Is this written as a scalar or a vector?
Scalar.
Yeah, it looks like this is a scalar. So there's some small thing, right? This should be a vector. So we'll have to take a look at that. So we might be missing some unit vectors in there somewhere, so we know which direction this is in. Anything else we should look at? All right, let's do the same thing here. Okay, so our result in the x direction, so we have 0, so dy of 0 minus ddz of 2xy ddz of x squared all right, does this look correct?
Yeah.
Yeah. All right, thank you, Mario. All right, so what is this one? What is this going to be? 0, right? This one should be 0. And what about this one? What should this be?
0.
This one's also 0. And this one?
0.
This one should be 0. And this one? 0. And this one should have a value. What's the value on this one?
2y.
2y.
2y. And what about this one?
0.
0.
Nope, this one's 0. Okay. So z. All right. Does this look correct? How many of you got this?
Got the same.
Okay, 2, yeah, at least 2.
Same.
Okay, 3. All right, awesome. Okay, so thanks for putting out the work. I think looks like you're pretty close on this one. Just a couple things. I think the main thing that you should all remember is think about for each one of these operations that we perform, make sure to have it in your mind whether or not you're going to arrive at the vector value or the scalar value. It's a very easy mistake to make, right? But the difference is actually pretty big, right? Because the difference is between a vector field and a scalar field. And so definitely for the quiz and the exam, make sure that you are including those vectors. And a good way to do it, right, is just take a look at that cookbook. Here, let me change the screen to that. But just take a look at the cookbook and you can see, right, so even though these are for the vector operations, right, we can see from here, right, on the solution, okay, there is that vector here, here, and here. So this one must be a vector valued outcome when we take the cross product, which we call the curl when we take the del cross a vector. And then this one, right, the divergence, okay, we don't see any of these unit vectors, nothing with a hat. So that one's going to be scalar. All right. Now going back to our work, we were asked, okay, about this. So should we call this irrotational? Should we call this vector field irrotational?
No,
Yeah, no.
or it's a non-conservative.
And I think, possibly the reason for the confusion, I should probably change this. This really, it's kind of hard to see. I might have actually had it correct. So this sometimes, if you have this, right, sometimes it's written as 0, but the 0 is bold, which is hard to see. So maybe a better way to look at this would call it like this, which is sort of a shorthand notation saying it's 0 in all directions. We won't run into this too much, maybe not even again, but there's sort of a shorthand way of saying, just say, oh, it's a 0 vector. It just means it's 0 in every direction. Okay. All right, so that's how you do each one of these. When you go on to these ones, don't forget, be careful to note, in cylindrical coordinates and in spherical coordinates, these products are slightly different, right? So they do have, make sure that you're using the correct operation when you go into the spherical coordinates and the cylindrical coordinates. Okay, so they're slightly different, and make sure that you use these or else you won't get the correct answer. Because this one, what coordinate system is this one going to be in?
Cylindrical.
Yeah, cylindrical.
Then this one should be in spherical. Okay, now let's go on to the next problem, or another problem. This one will take, is probably the most involved. Oops. One. Okay, so this one is asking you to verify Stokes' theorem. Okay, so Stokes' theorem is a relationship between a contour integral and between a surface flux integral. Okay, so if you think about this, right, if you have something like we're drawing here, we're looking at here. Okay, so this is a path through space, and we have some field that's in this space. So I'm going to draw, this is our path contour. This isn't, really accurate, but we can imagine that this is, let's just say that this is the vector field. This isn't exactly what it is, but this is the vector field, B. It's in the space. So we have a vector field in space, and there's a contour that goes around it. And we have a Stokes' theorem tells us a special relationship between this field and this contour. And that special relationship says that if we go all the way around the contour, taking the dot product with the field and add it all up, we're going to get some results. So what does that mean? That means that we're going to, right here at this point, we're going to take the field cross with this direction we're moving. So we're just adding it up all around here. We're adding the direction that we're traveling here. And we're looking at how much does the field point in the same direction? How much does the field point in the same direction all along this contour? Okay, and that's what this integral is saying. Take the field, go around the contour, and each place add up how much of the field points in the same direction as the contour. And then in the other direction, we're looking at this is a surface integral, right? We're looking at, okay, how much we have this information. So this is how much the curl, right? We have the field, the curl of the field. How much of it is going through the surface? So, right, this field, if we take the curl of it, remember it will be perpendicular. So it could be coming into or out of the surface, depending on where we're at. in it. And we're saying, okay, we should add up the curl all through this surface. So everywhere through here, we should add that up. And it's going to be equal. So this is a special relationship between the field and how you can add up the field around the perimeter versus how much is going through this. And so you hopefully you can think, get some kind of impression about why this might be the case. But this basically is telling us some relationship between the a surface integral and a line integral. And there's one in the video set that I gave you. There's one that describes this same thing. But what we call this is Stokes' theorem. So we want to verify Stokes' theorem for this situation. So I'm going to put you all into breakout rooms. Okay. Let's see, there are 6 of you. And I'll have you look at this problem. So solve both of those integrals. And in the homework, there's a couple hints to help you set up that problem. So I'll open those rooms now, and you can move yourself into them. And then I'll go through those rooms and talk with each group in the room. All right. How are you guys doing?
We are trying to solve the the problem with the hint.
Okay. Do you, was any of this, was this method familiar with you? Do you remember breaking like contour integrals into parts? Does this seem a little familiar?
Kind
I
of
have done it before.
vaguely. Yeah.
So I guess one thing to just that I think about, any integral, right? An integral is just like a fancy way of adding things together, right? So we can always just break these integrals into more integrals that we add together. So that's for part A, that's the definitely the first thing to remember. And then when you're doing this, right, each one of these parts, right, the DL is going to be slightly different, right? So we can have a, so when you make this integral to find DL, right, you can find DL for this loop, this segment, and this segment. And you can find those off the cookbook. And then also you can find the DS off of the cookbook by thinking about when you're on this surface, what's changing and what's not. Okay. So did you say you were working on B? This is the one that you're the most confused about?
We're working on A, I think. Yeah, A.
Okay, A, all right. So for A, right, you know what the field is, and you're just trying to determine what DL is going to be for each one of these. So to find DL, right, use this. And when you're in cylindrical coordinates, this is probably going to be the easiest one. Or this is going to be the one that you want to use, is choose your DL off of this. So this would be your DL. And the path of that is going to only be in one direction each time, right? So in this case, right, the R is constant. So you can determine which, so when you take that dot product, some things are going to end up going away for you. Does that make sense? Does that sound familiar?
Yeah. Yeah, it sounds pretty familiar.
Yeah, so the DL, you pull it off the cookbook, you take the dot product, some things are going to go away. And then when you take that integral, you're also going to end up, some things are going to kind of go away also because they're staying constant.
So good question. Despite the fact that from -2 to 2 on the x-axis is a straight line,
Mhm.
we still integrate based on that formula because they are all in the same shape.
Yeah, and also because let's see, when you're on, let's see, are you looking at this circle right now?
I'm just looking at that circle. I'm
Yeah.
using that to picture the problem.
Yeah, and
So-
that's because this contour goes in one direction. So it's a little confusing to think about, but if you tried to integrate from -2 to 2, you're going to get a different answer than if you integrate from 0 to 2 and then from -2 to 0. And that's just because of the contour.
So if we do that, which one is correct? So 1 from 0 to 2.
Yeah, so the way I set it up is I said path 1 should go from 0 to 2. Path 2 is from phi equals 0 to pi, where r is constant, right? So you're on a constant radius. And path 3 is a straight line. So the phi, the phi angle does not change. I believe this should actually be pi from -2 to 0. Okay, I'm gonna go to another breakout room. So yeah, just try making all 3 of those integrals and use that vector cookbook.
Thank you.
Yep, you're welcome.
I didn't finish it. It's
Hey.
supposed to be R equal to and C equals 0 to integrate with the rest.
Okay. So what I did, so 2 cosine. Oh, okay. So 2 cosine. The integral of cosine is negative sine, so it goes to -2 sine of phi, which, when integrated from 0 to pi, is 0. So that doesn't matter. Then sine goes to cosine. So how did you get that multiplier of 2 then? I think that's where I did something different. I don't have that multiplier of 2 outside of that cosine.
Oh,
Because the multiplier of 2 is only in front of, would only be in front of the would only be in front of the cosine before you integrate. And so
Right.
when you integrate that cosine, it goes to sine. Is that,
Well,
sorry, does that am I making sense?
yeah, but I think I got it because from the R sign, and when I integrated the 2 in it, I just moved it.
No, there is no R sign. It's just sine.
Oh, is it?
Yeah.
Oh, I guess I might did it wrong.
Well, no, you did it right, except you just take off that 2 multiplier and it's just 1 plus 1.
Hi guys, how are you doing?
Pretty good, I think.
You can't be
So
used.
I think that's the thing that you're probably might be getting confused on or seeing is that when you have that that second integral, you're going around the loop or that outer part. So you're on that semicircle where the radius is equal to 2. And so the R is going to be a constant. And that, I think that might explain where your confusion about that 2 multiplier comes from, Calvin.
So, are we supposed to have that 2 multiplier in front of both of them? Because there's R cosine and then there's just sine of phi. And that's what I'm talking about.
Okay. Yeah. And that 2 is going to come from the DL that you choose. So did you determine, I'm not sure where you are in this, but how did you determine DL and the dot product of the field dot DL?
Oh, I don't think I did that part.
Okay. So that whenever you're setting up all of these integrals, I'd encourage you to, go to that vector cookbook and look that up. So on the vector cookbook, you'll see, a series of DLs. There's 3 different DLs you could choose from. 1 in Cartesian, 1 in cylindrical, and 1 in spherical. And so because this is a cylindrical problem, you'll choose the DL from the cylindrical, and you'll take the dot product of the field dot DL. And part of the confusion, AK, make sure I'm seeing here, I don't know if you can see my cursor, but you have this L2 and you have B dot DL, but you have no indication that those are vectors. And so lacking that indication is actually, it you know, without it being vectors and making it being scalar, that could be adding to the confusion. But also, you know, on a quiz or an exam, you would definitely need to mark that these are in fact vectors. So you take the dot product of two different vectors. So B is a vector field and DL is also a vector. And that will give you two different, when you do that, you're going to get a integral that has that you can do over two parts.
Okay.
Because one, you'll end up with a dr and a d phi. All right, okay, we're just about done here. I'm going to bring everyone back together. Maybe they all left, I'm not sure. Breakout rooms. I think they're just about to get assigned back in. So be sure to choose, when you're doing this, be sure to choose the correct DL. And the correct B. Okay. So hi, everybody. We can look at this again for a moment when we come back next week. I'd encourage you to take a look at this too, but remember, B is going to be a field, DL is going to be a field. You can take the dot product, R cosine phi, that's going to be dotted with R dr plus phi R d phi plus Z dz. And then each one of these is you're going to get three different integrals out of this where different parts are constant. So we'll look at that again, but see at this part, we're going to have some R part that is non-zero, some part from phi that's non-zero, but this isn't going to contribute anything. So we're going to end up with this R cosine phi dr plus R sine of phi d phi. So this is equal to BDL, which occurs in all three of the integrals. So in this, it'll occur in all three, and the only difference is going to be the limits, and the limits are taken from here. All right, sorry, I went a couple minutes over time, but that's how you do it. Take a look at it if you can today or tomorrow. Enjoy the long weekend. Watch the Coulomb's Law videos, and see you all next Tuesday. Stick around for a few more minutes if anyone has questions. If not, feel free to take off.
To clarify, Dr. Chrysler, we are keeping the variables that are changing, right? Not the ones that are constant.
Yeah, so let me show you. Oops. We can look at this again for another minute if you would like. Okay, so now we've performed this b dot dl. And so we have 3 integrals we want to do. So L1, we have phi equals 0, right? And R goes from, so if I do this, take this integral, we could think of it this. Oops. Sorry. And on this one, right, phi is 0. So that
But for this one, why do we have 2?
Oh, why 2 integrals? Because of this. So each part of this is different. So maybe let me back up a little bit, make this. So this is,
Oh, that's from the question, right?
yeah.
Oh, sorry, my bad.
Yeah, and we're trying to do this integral. Yeah. Okay, so that's where this comes from. And so then because there's one part that's dr and one part that's d phi, you'll yeah, get that's where that's going to come from. Okay. All right. So then when you do this integral, right, for r, we're integrating r limits. So for the limits on r, right, we should go from 0 to 2. But what about for the phi limits? What should the phi limits be?
Phi at that point is 0 and it's not changing.
Yep.
We have it. Oh,
Yeah. So that part is not going to be changing at all, right? We're integrating over by d phi, but the angle is not changing at all. So this part ends up going to 0 because of the limits. So this one will have, this is the only one that's going to give us some result. Right. So we should have something, right, like and then what is phi in this case?
0.
Yeah, phi is 0. So 1/2 r squared. And then cosine of 0, that's 1, right? So really, we're just doing 1/2 r squared. So that is equal to 4/2 minus 0. That look right? That looks right to me. Does that make sense?
Yes, it does. So instead of just like for this example, I just took out the second equation because like p was 0. So we should still try substituting to see if we'd get something out of it first and not just assume that because it's equal to 0, we don't need it.
Oh, should we actually do this integral?
Yes.
Oh,
That was my question, because like some values are changing, some are not. So should we like
let's see. That's a
just
question.
take out the values that are constant and work with the ones that are changing?
For some reason, I'm having a little bit of trouble visualizing in my mind right now, but because we're integrating by d phi and the limits are 0 to 0, we're always going to get an answer where it's evaluate at one place and then subtract the same evaluation, which should be 0 every time.
That works.
I think for some, let's think about this. If you have a moment, we can think about this again for a second. I think that'd be like, let's say, let's integrate x dx, but let's go from 1 to 1. Let's see what happens. All right, so we're gonna get 1/2 x squared, right? From 1 to 1. And so this is always going to give us something like this. 1/2 1 minus 1/2. And no matter what this is, right, it's always going to be something like a minus a, which will always be 0. Because we didn't actually move at all in this differential direction. That's what I'm thinking right now.
Yeah, that makes sense.
You could of course do the full thing, but it's a little unusual because this is the differential direction that we're adding up over, and we didn't actually move at all in that direction. So therefore we shouldn't be able to add anything up in that direction since there was no movement.
Got it.
Yeah. Okay.
That helps. Thanks.
Cool. All right. Yeah, no problem. Everything going good in the class so far, Daniel?
Yeah, it's been all right. The videos you send help a lot. So
Okay, that's good. I hope, I try to make it a little bit different than the other classes. And I know for me, it's a little weird, but it's hard because most of you are in Pocatello and I live in, my main campus is in Idaho Falls. And I feel like we can actually interact a little bit more on the video rather than when it's like that really small screen and I can't even see your face, Yeah.
yeah, this is better in my opinion, actually.
So,
Especially with it being a small class. So
yeah, and that definitely helps a lot. There's only a few students in here. So
thank you.
You're welcome. Have a great weekend.
You too.
All right, bye.